Hello, it's Miss Wesley, and you guessed it, it's calc time. Let's look at definite integrals packet page 14 for these examples. Today is more of a physics discussion. We're going to have calculus meeting these concepts of position, velocity, and acceleration, which we've talked about at various points during the year. And speaking of which, here's a question. Hey guys, how would a bunch of astronomers organize a party? Well, it's simple. They would plan it. Now we got to think back. I mentioned that we've talked about these concepts at earlier points in the year, namely in our unit on differentiation. And I want to write a few facts at the top. We had a few abbreviations for some of these concepts. We called acceleration was A of t, velocity was v of t, and position was actually s of t to us. And you can take derivatives to go through this chain, right? The derivative of velocity, the rate of change in velocity, is equal to acceleration. And the rate of change in position is equal to the velocity of the function, right? The double derivative, second derivative of position gets you all the way back to acceleration. Well, now we want to go the other way. I notice in 12 and 13, you're starting with things like acceleration and velocity, and you want to go backwards to get to the position function. So here is the connection we're going to make using integrals, right? If this fact is true, then also I'll say, therefore, you can go the other way. If you want a position function, well, that's going to be the antiderivative. We'll go indefinite integral of the velocity function taken with respect to t. And that would be two derivatives of an acceleration function. I'll write a double derivative here of an a of t dt. So here's what I mean. And I think a good example to start with is 13, because you're given acceleration, you got to go backwards 2 levels to get to a position function. So not only am I going to have to integrate once, I'm going to have to integrate again. So it's lucky that I'm given a couple initial conditions. This should, if any plus c's pop up in this particular question, I should be able to take care of them with those initial conditions. So step 1, right? This will be a 2-part process. Start with acceleration. Let's find velocity. Let's go back 1 level by taking the antiderivative of acceleration, 4 minus t, taken with respect to t, like that. So this should work pretty well. This is an indefinite integral, like I said, no limits of integration at the top or bottom like there are in the rest of this packet. And let's integrate. 4's antiderivative is 4t minus the antiderivative of t, which is t squared over 2. And then the plus c reappears. Oh, how I missed it. But that's because this is indefinite. Well, not for long. We know the velocity at time t equals 0 equals 8. Let's plug into there to get the constant of integration c. So 8 is the velocity when all the t's become zeros. 0 squared over 2 plus c. Really, this is 0 and that's 0, so 8 must equal c. So this gives us a velocity function. Therefore, we'll say v of t equals 4t, we said, minus t squared over 2 plus 8. So keep this in mind. Our work isn't finished. It says we have to get a position function, right? So we're going to actually anti-differentiate again, take another integral. So here we've got to find s of t, which is the antiderivative or integral of v of t. So 4t, I'm just using the same answer we just got, minus t squared over 2 plus 8, taken with respect to time. I'll put a dt at the end there. Let's go to it. Okay, so 4t's antiderivative, it'll be 4 over 2, so 2t squared for the first part. Try the next two. You have a 1/2. We're raising this to the third, so 1/2 times a third, 1/6 t to the third. Check that for me. And then plus 8t plus c once we've integrated. Now it's time to get c, and we can be done with this, right? We have this second initial condition that the position at time 0 equals 0. So 0 equals a bunch of zeros again this time, plus c, and your final c, I should have called it c sub 2, equals 0. So final answer is this position function with 0 plugged in for t. S of t equals 2t squared minus 1/6 t to the third plus 8t, and then just a plus 0 that we can leave off. So if this whole process worked with derivatives for us before, it can work backwards with antiderivatives for us now. Okay, this question about Reagan driving her car. I want to star this a couple times because this is a position, velocity, acceleration question that's given to us in a much different context than we've seen before. I want to label that this function is the velocity of a car driving up and down a north-south highway, the car's velocity. Up is always going to be positive velocity. Down, we'll know she's driving down or south if we know velocity is negative. Another thing I would copy in this little free space is what you're going to see underneath in questions 14 to 19 are some physics terms like displacement and total distance traveled. So just as a reminder, if we take the antiderivative of velocity, it gives us position or displacement. The integral of velocity is going to equal that vocab word, displacement. So basically how far you are away at the stopping point from the origin, distance from where you started, versus if we considered all of the total distance traveled. I'm going to put absolute value signs around that velocity function, and this will be what I said, total distance traveled at a specific point. I'm noticing when I just gaze at this picture, there's a bunch of time from time, what are we counting by? So from time 0 to 30, you've always got a positive velocity, right, in between there. So she's always traveling north in this realm. And then from 30 minutes all the way to 55 minutes later, this is all below the x-axis. So you're talking negative velocity. She must be traveling south for a while. And if you just take the absolute value of all that, you'll see in a second, it'll take into account your total distance traveled. Okay, first it says, can we just read the graph? 14 says, when is the velocity equal to 0? We can make a list of those times. So find me any x-intercepts of this velocity function. At 0 minutes, velocity 0. I'll just circle it there. Where's the next x-intercept? Again, velocity 0, 30 minutes later. So at 30 minutes, velocity 0. And lastly, at 55 minutes, you have another time where you're hitting the x-axis. What's happening to the car at these times? You can give me one of two phrases. You can say the car is, quote unquote, at rest at these times. Really not moving because velocity is 0, right? The speed of the car is 0 at those times. More practically, we can say the car is changing direction from north to south, since we're only going one of two ways at that time. So really at time 0, the car's probably starting up. She travels, increasing speed for a while, stays at a constant speed for a certain amount of time, and then speed is decreasing, but she's still traveling north. Her car must turn around here because now we're changing from positive velocity to negative. And again, if this experiment continued past the 55, who knows? Maybe it would continue up past the x-axis up into the north realm later there, and she'd be changing direction again. Okay, so that was just reading the graph, the x-intercepts. Now let's get into the calculus. Circle this one. Can you calculate? We're getting right into it. The integral from 0 to 40 of the velocity function. This, according to our key, gives us displacement. That's going to be the meaning of our result. Let's look at the picture. Integral still means, like it always has in this unit, area under the curve. So this area all the way up to 40 minutes later, I'll just draw a red line there. We want the total displacement. We want to add the area of, this trapezoid to the area of this little triangle that's below the x-axis. Why don't we fill in some areas now? I have a feeling we're going to get asked a few more questions about areas below the curve. We can do average base times height for area of a trapezoid, and notice the scale isn't by ones. So the two bases, this is going to be 10 to 15, so 5 minutes long. One base is 5. The other is 30, 5 plus 30. Average those for that trapezoid times the height. The height here, the scale looks like you're counting by every tick mark is 20 meters. So the height is 60 meters. We'll say times 60. So this area above the curve is going to be 1050 meters. Okay. Now let's just get this little right triangle here, and we'll use 1/2 base times height. So 1/2. The base, I'll call it this here, which will be 10 minutes. So 10 times the height, which is going to be 40 meters. And it is negative. We're going to consider this area to be negative. And 1/2 times 10 times 40 gives you 200 below the x-axis. While you're at it, you might want to fill this in, since another question is going to be asking you all the way to 55 minutes. It'd be 1/2 in here, 1/2 times the base. The base is going to be 15 minutes. and the height is going to be 40 in the negative direction. So for later, we'll use that this area is going to be 300. Well, two of those numbers can get us the answer to 15. 1050, which is the displacement from 0 to 30 minutes, area under the curve. And then I'm going to say minus 200, since we want to count this area as being negative. Since you're traveling south, you're below the x-axis. So you could say this final answer is going to be 850, and since this is distance traveled, we'll put the units on there of meters. Explain the meaning of the result. This is your displacement. We'll say from starting point at what time? 40 minutes into the experiment, so at 40 minutes. We're not saying she traveled 850 meters because she actually traveled more than that. She traveled some north and then some south, but this is how far she is. If she freezes at that point, she's this distance away from where she started. And since it's a positive, you can say she's north of where she started. What is the car's position at t equals 30? So 30 minutes later, what's the position of the car? Position is displacement. We actually have this one labeled on the picture. That's just this trapezoid worth of traveling. So at t equals 30, we can say she is, and if you want to draw this out, this is 0 to 30, the integral of v of t, taken with respect to time, is just that 1050 meters. That's her position. Right? She's traveled 1050 meters north of the starting point since this is positive. Okay, 17, find Reagan's total distance traveled over the entire time period. You can look back up to your graph. The way you'd write this out notation-wise is 0 to 55. That should be 0 to 55. Not of v of t, we'll say of the absolute value of v of t, dt. And that's just, we'll use those absolute values this time because this one says total distance traveled. Any negative or positive distances, we're going to count their absolute values. So this will be the 1050 plus the two negatives, but we'll count them as positive. So the 200 meters and the 300 meters as well. So she's traveled total in the entire time period, 1,550 meters. Okay, let's take a look at 18 and 19 here. These questions about at specific points in time, is the car speeding up or slowing down? I went up to the graph and I just circled the two spots where this is going to happen. So here's t equals 25, where our velocity is, and here's t equals 35. And we want to choose. We want to think about velocity versus acceleration. Now, what about at t equals 25? Can I ask you some questions about that? At that point, is the car traveling north or south? The car's traveling north at this point because you're still above the x-axis. You've still got a positive velocity value. However, the velocity is positive, but it's approaching 0, right? This acceleration is going to be negative because basically velocity is decreasing at that point. So I'm going to pick slowing down for number 25. I'll go down here and choose it, slowing down. And my reasoning will be that velocity is positive. It's greater than 0, but velocity is approaching 0, or decreasing. 0 there. So like we used to say, you have a positive velocity but a negative acceleration. Those two are not working together. How about at t equals 35? Let's check. So at t equals 35 minutes, the car has taken a turn and now we're in the negative realm. Now we're traveling south, so we have a negative velocity, but check it out. We're still in a downswing of the velocity curve. That means velocity is getting increasingly more negative. Acceleration is negative here and adding to that. So we'll say here speeding up, and we'll give a reason for it. We'll say v of t, velocity is less than 0, and velocity is getting increasingly more negative. So is getting, let's say increasingly more negative. So I don't know if this brings back memories from earlier in the year when we used differentiation to answer a bunch of these questions, but here are a few examples of ways that integrals can help us. Okay, catch you soon.